Welcome everybody to the 11th lecture unit. Today we'll be dealing with the chapter 7, optimal control. As you've seen until now, control designs were much concerned with pole locations of the closed loop. We established the notion of stability for linear systems with pole locations, with the right pole locations. If you remember in the basics course, we could say something about absolute and relative stability, and that was all based on pole locations, where they should be in the S-plane in that course. Here in our course, in the Z-plane, and up until now we had several control designs, all speaking about where these poles should be, respectively the eigenvalues and the state space. But the same thing. We used these complex quantities to encode basically the behavior of the system that we would like to have. And then we designed a controller that achieves that. Optimal control is different in that sense. We will not be concerned, although the mechanics under it, the state vector feedback, for example, that we will encounter, that works, of course, in the same way as up until now. But the difference is a paradigm shift. We look at the problem from an optimization point of view, at the control problem, and not as coding a response and response times and so on. And the reason for that is basically you can look into many processes in nature, and there an amoeba or our blood circulation system and so on, all these systems out there, they certainly did not do analysis on with pen and paper and came up with pole locations. But what happens in nature frequently is some sort of intrinsic optimization, some efficiency seeking. So basically that is visible in many natural phenomena, has even spawned evolutionary algorithms, for example, where we as humans in technology, we try to mimic natural processes of selection and of optimization to actually solve numerical mathematical problems. Now, I told you some 1-2 lectures ago that the optimal control as we know it today found its beginnings in the space race, essentially, in the 1950s, 1960s. And I like this saying that the controller that we will look into today, the optimal controller, the LQR, as it is abbreviated, basically brought us to the moon. As far as I know, that was a controller that has been used on the first space flights, including the Apollo missions, and has been proposed in these lines. People then actually needed controls which are efficient in the sense of fuel efficiency and efficiently accomplish a certain task. There are some names that you may have heard of or that will come up again and again. And these names include, for example, we listed some of them here: Richard Bellman, Lev Pontryagin, in that time the Soviet Union, and Rudolf Kalman. Kalman and his famous, the filter named in his honor, the Kalman filter, is one of the most widely used algorithms, I would say, that have to do with optimal control or optimal estimation. And in each cell phone, you have probably several Kalman filters alone to filter and to post-process signals like like GPS signals and so on, and essentially locate your phone in a three-dimensional environment. We have this optimal control has been used now for many decades in many different application settings in different branches of industry. For example, yeah, you see here some examples: aerospace and process control, robotics, economics, etc. The digital computers, when they began being available, you could do more and more interesting problem solving in real time. And that also includes solving optimization problems, even in real time. What we will do today is look into the basic principles of optimal control and establish a basic understanding of what actually goes on there. And to start with that, essentially what we need when we optimize is our main focus of study, our main thing that we optimize is actually some function of some variables. We just cast it down into this simple mathematical terms, into this mathematical framework. So the function that we look at and that we actually have to design as control engineers is what we will call an optimality or a cost function, actually a cost functional. And we want to optimize the value of such cost function according to some criterion. So for example, if this function contains several terms which are added together in some weighted fashion, we will see what that means and how we can work with such a function. What we want to do, or what we want to solve for, is we want to find, for example, those control inputs that minimize such cost function. So cost can be written down as actual monetary costs, but also we can conceive costs in some more general way. For example, the deviation of where we are in the state space or where our output signal is with respect to our reference. So some measure of a control error will come into play here, and we will formulate that in terms of costs. And costs have the property that when they are large, it's basically bad for us. That's an unfortunate situation. And if we manage to drive down costs towards a minimum in costs in this cost function, then we are in some sense efficient. And that's what an optimal controller's task is to do. Now we are, we are concerned here with discrete time systems. So we will come up with corresponding formulations in a discrete time setting. So we have a set of difference equations that describe how our control variables, that's our control input values, affect our states and our outputs. So essentially we will work in the state space, in the understanding of the state space representation, and we will formulate some cost functional and then we'll formally minimize that. This is basically done by Pontryagins minimum principle. Sometimes in literature you will find Pontryagins maximum principle. That's essentially the same. It's just that it was in original literature often called maximum principle, and the only difference is really the sign in the function that is being optimized. In that case, it was a utility function that you want to maximize, that you want to have as large as possible. If we negate that function, then we can see it as costs, and we want to minimize this cost function. And then we call it the minimum principle. But it's exactly the same principle that realizes the same task. Now let's look into the formal definition of how we can solve such an optimal control problem. So first of all, we need a cost function, and we decide for a cost function for now in a very general manner. So V is our cost function, a cost functional, which depends on inputs at various locations in time and on states. That's the initial state here, and then we have many inputs as a sequence of inputs over time, and they together allow us to assess which states at the particular time levels we will get. We look at several time levels, and here you see how we formulate these costs, and still in a very general way. we have a counting index I that we sum up over I from 0 to some horizon length n, capital N here. So that's the number of samples plus 1 that we consider. And over these time instances, we sum up a function L here, lowercase l, which is a function of some states x, of inputs, and maybe of time itself. So this L here essentially formulates a cost given on or defined on the state, on the current states and on the current inputs that drive the system. And it could be time dependent itself as well. But for the time being, we will not specify more closely what L actually looks like. The nice thing about Pontryagin minimum principle is really that once we've defined our cost like that, we can work with this general definition and get some very general but important and useful results how an optimal controller actually looks like. Then finally, we also take into account some term which only depends on the last +1 state value, x at the time, just one time step after the end of that horizon summation here. And m is just another function that expresses cost value based on the state values that we have at the last considered time step. And well, what is also important in our setting here is that these functions are non-negative. In fact, we consider them as positive definite, which means here L and M are considered positive definite, which means that for any valid arguments here, x and u and sometime k, except for the case that all states and inputs are 0, then we can allow the function value to be 0. But otherwise, we require that then the function value of L is always positive. So that means that if you sum up these positive or non-negative values, then we always will get some positive or non-negative cost term. Okay. Well, we of course cannot just optimize this system here, or this function here, in u and x of k alone, because we have x at the future times here as well, and they of course depend on the initial state x of k, and of course on usually on all the input values over time, and they depend on that by our model of the system. Our system dynamic model needs to be incorporated into this optimization now, because otherwise it just doesn't describe our system properly. So we will have equality constraints in this fashion here. We will have for each time step in the horizon, including or up to this time level k plus n plus 1 on the left-hand side, we will define these equality constraints, which means that the next state in our time horizon is some function of the current state, the current input, and maybe time itself, if you want. So that's a very general definition. It actually supports nonlinear dynamics here. F could be a nonlinear function of x and u. And also we define that the initial state x of k corresponds to the value of this x of k plus I, where I equals 0, of course. So this initialization, if you want, and then the connection, the difference equations here given by this equation 7.2, that has to be fulfilled. And under these conditions, we would like to find a sequence of u's, of input values, that could also be vector values. Everything is written here as vectors. So that's a vector of several input variables, a multi-input system, the multiple states here. And this function itself is a scalar function. So all these functions L and M here evaluate to some scalar cost. And then we just want to minimize this summation of scalar costs. Okay, now, if you remember from mathematics courses, we can solve an optimization problem, minimize phi subject to equality constraints like these here by using the Lagrange formulation. And we do that by first formulating a Lagrange function, which is essentially the objective function itself. So this cost function is, of course, part here of the Lagrange function. But then we subtract, in this case, that should be, read this please as 1 minus. So it's v minus the sum of, and then we take new variables in here, p, which is also a vector and is time dependent here. So p transposed, and then we multiply that by the implicit form of our equality constraints here. So these equality constraints up here are just made implicit by subtracting f from both sides. So we get x at the next time level minus f, that put to the left side, equals 0. And this implicit left-hand side of this constraint 7.2 is this parenthesized expression here. So whenever this is 0, of course, that the constraint is fulfilled, and then also the value of the Lagrange function is the same as the value of the objective function, the cost function up here. But by this trick, essentially by this extension, we will be able to formulate this dependency between the time levels into the optimization problem properly. So essentially what we did now was we changed an optimization problem of this cost function subject to a bunch of equality constraints into a new Lagrange function expression here, and we solved the same problem as solving the constrained problem up here by solving the unconstrained minimization of the Lagrange function. That is the strength, and that's why we do follow the Lagrangian approach, because we simplify the necessary approach, the method to solve such an optimization problem from an optimization problem where we additionally have to consider equality constraints and do a complicated constraint optimization. Now we changed into the Lagrangian, with the Lagrangian method to obtain a different function. This function has been made more complex, but it's sufficient here to solve it in an unconstrained fashion. So we minimize curly L here without considering constraints any further. We have to minimize now with respect to U sequence and the P sequence. These P's here are additional decision variables for the optimization, and it's a sequence of them over the time here, and it's a vector to be compatible with the number of states that we get here. That's a vector residual, a vector of zeros in the case that it's fulfilled, and it has to work out. So n many components have to be in P. And P is, of course, called the Lagrange multiplier. Okay, so how can we deal with the minimization? How can we get to minimization of such a function? First of all, we insert our formulation from above into the value or into the cost function here. So that's this, this expression here. And also we get M. So this expression, the sum over the L's, that's the stage cost, it's sometimes called. And then the terminal costs, M here, are the costs on the final state. And then we have this expression here from the extension to the Lagrangian. All right, so that's what we have to minimize for. And now it's we can argue that from variation theory, for example. When you look at this function, that's a function in U's and in P's, and essentially it's also a function in X's, in the X sequence here. And so what we can do is we can express the variation of this Lagrange functional as delta L, and then we can write down a full differential here, or this variational form with respect to the X's and the U's, and we will get the expressions of the partial derivative of dl over dx where we have to understand that we derive L here, curly L, with respect to one particular x k plus 1, k plus I. Okay, so that's necessary that we really keep track of which index we mean here, and then times delta x k plus I gives us this first order variation with respect to delta x. The same term comes up with partial differentiation with respect to u times the variation in u at time step k plus I. And since delta x k plus I and delta u k plus I are mutually independent, they can occur in a variation independently, because delta x k plus I does not depend directly on delta u k plus I at the same time level. Instead, it depends on the earlier u's and the earlier x's. So in order to find that location in u and x and p in the end, where the variation of curly L vanishes, which is set equal to 0 here, we will see that these are all independent quantities. We will need to have these partial derivatives 0 everywhere. And that's true for the partial derivatives with respect to u and with respect to x at each time level that we consider, I from 0 to capital N. And that gives us these equations here. So that gives us individual equations. So a lot of strong equations pop out here. In the end, these variations are independent of each other. So the entire variation term has to vanish, but that also has to be the case for arbitrary variations in x, respectively in delta u. So the coefficients have to vanish. And after all this line of argumentation, we will get to these neat little formulas that carry a lot of meaning, and they actually are necessary conditions, first order necessary conditions to solve the given optimization problem to optimality. If we find locations in the state space X and values U in the sequence, in the input sequence, where we can be sure that these partial derivatives vanish, then we have a candidate for an optimal solution that achieves both. In the first place, it considers the system dynamics and it minimizes the cost function. So that's a pretty hard result that we get from here, and we were completely general now in the sense that we took a general formulation of the system dynamics F, which could be nonlinear, a general formulation of the costs M and L, the cost terms here, and we could establish that these necessary conditions have to be fulfilled. Now, we first of all, we have to come up with the derivative terms directly. So we are not done yet. It's just that that's the lines that we will follow now. And let's do some work in differentiating the actual terms here. So first of all, we'll start by differentiating curly L with respect to X. That will be these terms here. So we'll get in the summation, if you remember, let's just scroll up here. If you look at this form here, 7,4, you will see that we sum up over individual stage costs here, individual points in the timeline of our horizon. So we have L, which depends on xk plus I. That's now what we want to derive with respect to. So there will be there will be a part with L, x of k, u of k, and k. Then there will be the next summation term L k plus xk plus 1, uk plus 1, k plus 1, and so on. If we now derive with respect to some particular x at k plus I, then all the partial derivatives where x k plus something else comes up will just vanish, and only this one particular derivative dl over dxk plus I will come up. So that's this first term here that you get here. So that's dl, and it's really only we derive with respect to one particular choice of dxk plus I, and only that term in the numerator or in the up here where we take differentiation from appears. Then if you look again into the full function here, we will get terms for, again, for x k plus I. That's now what we're looking into, this differentiation. So that basically pops up here in this structure in two different terms. First, in the term where we actually have this k plus I coming up here. The derivative of xk plus I plus 1 with respect to xk plus I is 0. That will drop out. And we'll get the derivative of df of xk plus I over dxk plus I, which is multiplied by p transpose k plus I plus 1, right? That's this term here is treated as a constant when we differentiate with respect to k plus I. So we'll get, let's just look for this term, we'll get this term here, which is p transpose k plus I plus 1, df at k plus I over dxk plus I. And then we'll get one more term, namely that term where we are one counting index lower than the one that we are differentiating for. So let's say we differentiate for k plus 2. So with respect to x of k plus 2, then for I equals 1, we will this one will evaluate to p of k plus 2 xk plus 2. So there is an xk plus 2 in here, and we derive with respect to that particular x. So this p here will come down as the partial derivative for that term. So for this summation, since we have two different time indices of x's coming up here, we will also have two entries in our derivative of the entire function with respect to some particular xk plus I. And that's this second term here. You see that it's different in indexing by 1, and it just picks out the time index with respect to which we did the derivation. So that's differentiating the entire curly L Lagrange function with respect to xk plus I. Now we do the same essentially for the derivative with respect to uk plus I. Also here, we will get these terms. This term here is simpler because it really just the equivalence or the corresponding term of this term up here came up down here where we have the matching indices. Sorry, I just see that here is actually, it should be k here. All right, finally we have one more. If you look at this last term, it never showed up until now, simply because we looked at earlier x's. Now if we look at xk plus capital N plus 1 and derive with respect to that, then we will get this m term or the partial derivative of that. And that's this last term here, the partial derivative of dm xk plus n plus 1 over dxk plus n plus 1, that comes up. And at this time level, we'll get some coupling with this term here. So the last term of the summation will give me terms p transposed k plus capital N plus 1 times x plus of k plus capital N plus 1. And then some older stuff, but this will drop away in the derivation, and we derive with respect to xk plus N plus 1. So we'll get this term, this p transposed as well here, and that's this last term. Now we actually worked out what these partial derivative conditions here mean by looking for our concrete form of the Lagrange function. And now we have formulas, still we have partial derivatives of our cost function terms here, so the L function in here, and the system df over dx, respectively df over du, that's what we still have to compute for some particular system dynamics that we get or that we have, and also this term. But other than that, these bunch of equations and the upper equations are formulated for any I within the horizon from 0 to capital N. So that's not only 2, but it's actually 2 times n plus 1 down here. So all these equations are a lot of relationships that we have to fulfill in order to be optimal in our control problem. But the point is, these derivatives are typically simpler equations, simpler in structure than the original problem even. So for example, if you have a quadratic form, as we will have afterwards in the concrete optimal controllers that we will look at, we have some quadratic control error, for example. So this L could be a quadratic function. And then if we derive a quadratic function which is quadratic in x, with respect to x, we will end up with a linear function. So in the end, what will come up is actually, in our cases at least, that will become relatively simple expressions. There are many of them and they are coupled, but essentially we will get to a bunch of linear equalities here, which are equalities in unknowns such as u and essentially p. And we will solve for these unknowns. A linear system can be solved if it's well defined. Think of our analytical designs and comparison of coefficients, or of the Diophantine equation actually. There we already solved linear systems by just using standard tools of computer algebra systems. So once we've done that, you will see that we get to a well-defined closed form solution in many cases for the optimal controller. And let's just go that step. Let's just go that step and specialize our results now. So that's the most, or quite general results, let's say, for the structure that we've seen up there. Maybe one more thing that's where I want to draw your attention to is that essentially these conditions are essentially formulated here at one single instance in time, and these ones are, as we'll explore now further, just coupled in a very easy to work with way. So that's all terms here which live on a particular time instant, k plus I in this case. And also this part here and this part here. And only here we have a very specific coupling of one term at a different time level, but it's not that we couple time levels all over the place at mixed time steps. That would be vastly complicated, and that would amount to a very difficult optimization problem that we cannot simply solve like that. Here we can actually find systematic ways to solve this optimization problem. What you see here in mathematical terms is actually a coupled boundary value problem, because what we get is essentially we'll get x of k is given, and from 7, 8, from this equation down here, we will essentially get p at time k plus n plus 1, because there it is explicitly given once we can evaluate this part here. This part is equal to pk plus n plus 1. So for p, we have a terminal condition, and for x, we have an initial condition. So that's why it's a boundary value problem. In fact, it's a 2-point boundary value problem given with parts of the variables, namely the x's, given at the initial time, and another part of the variables, namely the p's here, given or defined at the very last spot in time. And the problem is that it's coupled, and that makes a solution still laborious, still we need some effort to solve them. But let's have a look when we specialize now to less general dynamics and less general formulation of the costs. And we'll end up with what is known as the Riccati equation. So we specialize to what we know by now quite a lot. We look at a linear state space representation of the system. So we have that here. We already know our typical linear system equation here. And we will look at the quadratic cost function. In engineering, quadratic cost functions are a great tool because they allow a lot of things to be solved relatively easily. One example is quadratic errors, the least squares approach in statistical estimates, for example, in data regression and so on. So in concrete terms, our cost function will look like this. We will formulate our cost function dependent on the sequence of use and on the initial state, as we are typically accustomed to have 1/2 as a factor here. Then we sum up over all the samples in our optimization window, in our horizon, and we start with a term that is quadratic in X. And a quadratic term means that we have the vector, that's now a vector matrix vector product here. And this vector is a row vector because it's a transposed X vector here. And this one here is a column vector. And in between we have a square matrix. So essentially this form looks like this. We have this 1 by n vector X transposed. Then we have the square n by n matrix Q. And then we have the vector X. And that evaluates to a scalar because, yeah, you just see that in the dimensions. So that's 1 times n, n by n, and n by 1. So why is that a quadratic form? Well, X obviously comes up 2 times on the left and on the right in this case. And of course, if you look at Q equals identity, for example, then what will happen is X transposed X will just be the summation over all X, let's call it Xj's, the individual components, 1 to n squared. So that's really the squaring of the components and adding these squares up. And if you have different values in the matrix Q, then you will have different weights being assigned to each individual component. And you can actually take in components, different component products as well. So that's just a more general form of what we call a quadratic form or a quadratic cost function. We also have the same form essentially established here for the U inputs. So for single variable U, of course, that we will just U squared times some scalar factor R. But also for vector use, it's essentially the same as for the X terms. We will have squares of the input magnitudes of the input components times some weighting. And we will see how we can use that afterwards, and we'll analyze in depth how this actually allows us to formulate control problems and to get an understanding of how the controller will act when we choose Q and R in some particular ways. Then also in the end, we will have the terminal cost 1/2 times X transposed at the last time instant times some matrix L times the X vector at this last time instant. Also the L matrix here, basically the same applies as for the Q matrix, is a square matrix, of course. And we will look at symmetric and positive definite matrices Q, R, and L of the respective sizes. Then we are in the same framework with a positive definite cost function as we've seen before. So essentially by identifying the terms directly, we can get into the same notation as above in the Pontryagin chapter. So the stage cost lowercase l here is just defined as 1/2 times this this term of the summation up there. And the terminal cost term is, well, just this term with L. F of x, u, and t is, of course, our right-hand side of our linear system equation. And now we can actually proceed to just insert into the formulas that we established above. And that leads us, after some substitutions, to the following forms. So what we will get is, that's now the final results of the last chapter, where we established the equations for p, x, and u as well. So you will recognize this last one, that's our terminal condition. So p, k plus m plus 1 is just the derivative of m with respect to x, k plus m plus 1. And you see that this becomes a very simple linear form in x here. Remember, if we take a quadratic form, of course, in the scalar case, it's clear what happens. In the scalar case, that looks like we have some 1/2 times some scalar L times x squared, and this x squared is at k plus n plus 1. And now we derive that with respect to x at k plus n plus 1. So let's take this one. We derive this expression with respect to this x, and of course we will get just L times x k plus capital N plus 1. And that's exactly what is written here, down here. That's exactly the partial derivative of this terminal cost function m with respect to this x here. That's just what happens. That's why we took in these factors of 1/2. So formally, at least, so that it vanishes here. And that's how we get the terminal condition directly. So we tie together the terminal state and the terminal value of the Lagrange multiplier in this equation. Much the same we do in the other equations, where we have established the connection between the p's at different time levels with the x's. And this equation here can actually be turned into an explicit form for p, k plus I plus 1. If we assume that we can invert g, then this basically looks like this, where the power minus transposed is to be understood as the inverse of g, and that's transposed. So if we can build the inverse of g, so that means in our case no deadbeat behavior, then we can do this reformulation here. Then we can explicitly write down a difference equation which tells me the next value of p given the current value of p and the current value of x. Okay, now we also can express the control input, which we see looks like some coefficients here, minus r inverted times h transposed, and then the value of the next Lagrange multiplier vector. So if we could just get the value of this next Lagrange multiplier, then we would know the value of u. And it turns out that Riccati was the one coming up with a simple solution to that problem, an elegant solution in that sense, which is known as the sweep approach or the sweep method. And that works by saying or by assuming that, well, let's write the Lagrange multipliers as some maybe time-varying mapping, some linear mapping here from the state. So we just proclaim that the Lagrange multipliers at a particular time level can be written as a linear combination of the states. And by doing that, we can solve actually, we can eliminate p from all the equations up there. And we will get to an expression which is given, which is where we can collect the values of x to the right-hand side. So that is true on the one part for u of k plus I, the actual control law. which is just this next value of s times the next value of x. So of course, the next value of x can be predicted by inserting our system equation. And since we have u k plus I coming up on the right side here and on the left side, we can isolate that to the left side and we'll get to a form where uk plus I is given as some more complicated coefficients here times xk plus I. And it turns out that this sk plus I plus 1 is also in here. So it's that's actually not such a simple form here. It's actually part of a matrix in here, a matrix expression that is being inverted. So it's definitely a nonlinear mapping here. So it becomes more complex in that sense. But let's continue our journey here. From the other equations, we will get p k plus I, which we can express as sk plus I, xk plus I, can be expressed entirely in proportional to x's, and this is the next x, so we have to insert again this form here, and we insert u that we just obtained here, so that's a lot of terms, but boiling that down gives us this line here. So we get terms, and I underlined here that these terms are always of the form we have some coefficient matrix here essentially times xk plus I, and xk plus I is always coming up here and can be collected to the right. So that means that this entire matrix vector equation here is scaled from the right by xk plus I. But it has to hold for any xk plus I, because we want a controller which is not only true, say, in the origin, but should behave properly and correctly everywhere in the state space. So the coefficients have to match up. And that's exactly this equation. We essentially eliminate xk plus I here, and we'll get an interesting difference equation. This difference equation tells us something about the evolution of this matrix S. S is a square matrix here, n by n, which is a function of time, or a matrix signal of time, if you want. And also, we have it written down in a way here that tells us a backwards difference equation, or that tells us the backwards evolution in time. So on the right-hand side, we have expressions of sk plus I plus 1, here and in here as well, in this complicated inversion term. So that's nonlinear, and that expresses the earlier value in S. So finally, what we can say from the terminal cost term is that when we insert that there, S is actually let's just do this quickly. We had before that L x k plus n plus 1 equals p k plus n plus 1. And that's all vectors. And now when we insert, we'll actually get that this one is s k plus n plus 1 times x k plus n plus 1. And hence we get to this expression that this has to hold true for any terminal state here. So the coefficients have to line up, and we know by now that the value of the matrix L, which we defined as cost term for the terminal state, has to be the value of S at the last time step, or the other way around, actually. By prescribing some particular value L here, we know that S at this time level has to be the same as L. And hence we can start from that time step, from one after the horizon length, and work our way by evaluating 720 here, evaluating that step by step, so we can evaluate earlier and earlier values of S here until we're at the beginning. And then it's just as simple as that. What we need here to evaluate u of k, which is the current control input, is actually some expression times s k plus 1 times g x of k. And actually here we have the explicit result. So we have x of k as the initial state, and we have S established now from the backwards recursion. And that's essentially how you can come up with the optimal controller in this setting, the optimal control law. So by solving this backwards iteration, starting at the last point in time here, setting it to L and letting it evolve over time until you're at the beginning of your horizon, then you can use this sk plus 1 that you had just one step before k actually, you can evaluate u. This is a state feedback controller. So you have some matrix expression here in the front, and you have the current initial state here, x of k, that scales all, that is being scaled here and transformed into your current input. And using these inputs, you solve the original optimization problem optimally. That's the key that unlocks this optimal control concept. Okay, that still looks relatively complicated in the sense that it's actually quite some work for a computer algorithm to evaluate all of that. Even though we have the prepared formulas, there are many steps that you need to take over the horizon and hence many computations that you have to do to arrive at the value u that you actually want to get, that you want to apply to the system. Before specializing that further and vastly simplifying it actually, yeah, that's actually what we'll do right away. So let's have a short look here. What happens actually when this horizon becomes longer and longer? Seemingly, when you look at this method here, you would need more and more steps to actually arrive at sk plus 1 and evaluate u of k. Gladly, when we actually go to n towards infinity, then what we're interested is actually not a step-by-step solution, but instead we would like to see whether these whether this Riccati equation, as it's called, this Riccati difference equation, has a stationary or a steady state solution. And if it has this steady state solution, then we'll see that the problem becomes much simpler. By the way, when we have one last look at this large equation up here, what we see is, first of all, that this equation up here does not depend on states. So we initialize with problem parameters in the end. We can pre-compute it essentially. So with problem parameters in the end, and then we make our way forward or backwards in time and evolve, compute S of k down to S of k plus 1, basically. And once our problem is fixed, our system matrices are fixed, and the weightings are fixed, this S of k plus 1 can be stored and will never change anymore during runtime of the controller. So then we have here a fixed feedback law, a fixed gain that we apply to the system with the current state. Okay, still in the pre-processing step, you have to do more in that case. But now let's have a look at this equation. This is difference equation. And if we manage to find a solution that where S does not change over time, then we are actually in the case n, in the limit case n towards infinity. So just think for a moment on some algebraic solution, in the sense that it's not a difference equation anymore, or it does not change from one time step to the next. Then we can replace S as a signal over time simply by some stationary solution S infinity, S index infinity, for example. And then this S at the next time level will be the same value as the S one time level earlier. And this equation is a nonlinear matrix equation, but that's what we call the algebraic Riccati equation. That's what you see here. So we just dropped every time index of S here. It's otherwise the same equation as up there. And we want to solve this equation now. Solving this equation solves the problem for an infinitely long horizon. So essentially you sum up from now to infinite time and sum up the control errors via the x squared terms and input contributions via the u squared terms. And you minimize all of that. So that's the so-called regulator case. You find efficient inputs so as to keep this summed up squares of inputs and states as small as possible if you sum up over the entire time axis. And it turns out that this actually, that's what we call the linear quadratic regulator, the LQR, for steady state control, respectively an infinite horizon controller. If you, let's say for the moment that we find the value of S, of the matrix S here, by solving this algebraic Riccati equation, then we will see that, or by just inserting into the more general expressions above, we will actually get this relatively simple form of a state vector feedback law. So we have U as minus some matrix gain times X of K. So it has essentially the same structure as the state vector feedback controllers that we have developed so far. Just we approached the problem now in a different sense. We formulated a cost function based on states and inputs and minimized that, and the result turns out to be of the same structure as generally as we have when we look at pole placement designs. Let's have an example for a basically pathological example when this does not work out. So for example, let's take this particular system, two states, and you see that these states have unstable eigenvalues. Why do we see that here? We have a diagonal form in the system matrix. So the state x1 is not influenced by state x2 and the other way around. So they live in their own modes. It happens to be the same eigenvalue. It could also be different eigenvalues that would not change our example now, really. Both of them are unstable, which is not a showstopper for control design, as long as we can access that mode properly. And now we're given an input effect, an input gain here of 0 and 0.5 times u of k. While this is fine for the second state here, the second state it will be possible to stabilize that, to design some feedback controller that makes this second state stable and decay over time. We cannot access the first state, and the first state just lives on its own by, it doesn't see anything of the second state, so it's not even possible to indirectly access it. It only lives on its own. And if we now happen to initialize the system with a vector 1, 0, for example, where the first state is not exactly equal to 0, then we can just compute the state trajectory, and it will turn out that this is actually blowing up to infinity no matter what we do. No matter how u of k is chosen, we will get x1 of k is just this exponential blow up 1.5 to the power of k, which of course goes to infinity exponentially. Now, if you insert, okay, that's an unstable solution, but if you insert that into the cost function with unit weightings here, Q is the identity matrix and R is 1, then we will get the value of the cost function now for an infinite horizon here is u squared, so 1/2 times u squared, plus x2 squared, plus x1 squared. And that's, since we know that we will definitely have this expression as x1, no matter how we choose u, we can just as well insert it here. And this will become 1.5 to the power of 2 times k. And that will, of course, be infinite, independent of the choice of u and x2. So we speak of a system like that as being not stabilizable, because our control input, U of k, does not have or cannot steer the first state actually anywhere in the system. It just happens due to eigendynamics. And this happens to be unstable as well. So that's basically the reasons. The first state is not controllable. This uncontrollable state is unstable. And the reason why we see infinite costs as well here is that we actually see the second state, the first state in the cost function. Of course, we could close our eyes with respect to that and have a 0 in the weighting matrix here. Then this term would drop out, and I would happily go on to design a controller which acts on x2, and this might be actually fine in the state x2, but the x1 part of the system just blows up. And in that case, we see that, so we will not get to some finite costs here. That's the case because the unstable state, x, actually both are unstable, but the unstable and uncontrollable state is mapped into the cost function. And a bounded cost function, or to achieve a bounded cost function, is only possible if the system can be stabilized. That means that we can access all unstable modes in the system, and also if the system, if the cost function also shows up all these instabilities. Otherwise, we do not get really the specifications into our optimization problem to do something against the unstable mode. So each unstable mode that we want to stabilize, of course, has to be mapped into the cost function, which we will call detectability. Okay, for stabilizability, yeah, we have this kind of definition here. A linear state space system in our standard form is stabilizable if all uncontrollable eigenmodes are asymptotically stable. Of course, if the system is fully controllable, then we do not have any unstable eigenmodes, and that amounts to stabilizability. So stabilizability is, of course, given, is present when the system is fully state controllable. But if it's not fully state controllable, it still can be stabilizable. And just in the case that, that we get unstable system dynamics, which is uncontrollable, then the system is not stabilizable anymore. All right, now how can we solve this algebraic Riccati equation, which is a polynomial equation, a higher order equation in a matrix? So it's already not easy possible here, but it's already more involved to solve it in a scalar fashion. Gladly here we get to a quadratic form, so we can solve a scalar quadratic equation in that sense. We'll do that afterwards to look at the weightings. But for the matrix case, that is not so obvious. So let's see how we can get to a solution to actually solve the algebraic Riccati equation. That is essentially done by MATLAB nowadays. There are good and various approaches of how to solve algebraic Riccati equations. And maybe to give you some feeling of why it is important to worry about all this structure at all. Why not just minimize some optimization problem with some costs in it, and as a result you get the first U, and that's your optimal controller. The point is that if you do not use this structure properly, you will get extremely inefficient optimization problems in which you don't even know whether you are at the global optimum. And it takes just forever to compute these optimization problems. Sometimes in some problem instances you have to go that way, but it turns out that when you think back to the space race and to the mid-50s, 60s of the last century, computer power was extremely scarce compared to today, of course. And so efficient algorithms were paramount that time, and are still, because it's just efficient to solve the Pontryagin problem or the Riccati equations, even though they have specific structure which is not so easy, like this higher order matrix structure. Let's just scroll up to that here. We have S coming up here, we have S coming up here, which is still fine, but then we have S coming up here and here, seems quadratic, but then we have an inversion in which S comes up as well. So that's actually a heavy nonlinear form here that that is sorry, this term here, that is not so easy to see how to solve it actually. But it turns out you can solve these equations, these algebraic Riccati equations, for several hundred states even as well, in a matter of seconds or fractions of a second. So since we usually don't need to do that in an online fashion during the actual real-time run, but can do that usually offline, that's no problem at all. It's not that today's computing power is of course extremely helpful, but it's just extremely efficient. There are extremely efficient algorithms to solve such Riccati equations nowadays. And that's in stark contrast to unstructured optimization problems, which die maybe after 20 or 100 variables. Of course, you can solve much larger problems, but it just takes more time and you have less structure and less guarantees. So long story short, let's solve the algebraic Riccati equation. We insert into some of our results from before to get to these expressions. So essentially we start out with this set of equations here, and we see that we'll get x of k plus 1, p of k plus 1, and p of k. So these two time levels, k and k plus 1, come up, and correspondingly we'll get x and p coming up there. So we can rewrite these two equations, which are themselves, of course, actually vector equations. Each side of the equality evaluates to a vector. We can collect x of k and p of k on the left-hand side, and x of k plus 1 and p of k plus 1 on the right-hand side. And by doing that, we'll get to this form, this tidied up form if you want. So we get a square matrix here of this structure times x and p stacked above each other at time level k. And then we get some different matrix, also square, times the next time level signals x and p. And that starts to look like that's an autonomous difference equation that ties two time levels together here. And we can solve such a linear difference equation essentially by a generalized form of the eigenvalue problem. Because let's just take the ansatz that each x and p vector signal here can be written as some vector which gives us some direction times some eigenvalue to the power of k. So mu is some eigenvalue to the power of k. That's nothing else than an exponential ansatz of a difference equation. Think of differential equations, linear differential equations. There we did, in order to get to the closed form solution, we do an exponential ansatz of the solution, and the eigenvalues there are of course the roots of the corresponding characteristic polynomial of the associated eigenvalue eigenvector equation. So here we take the same approach, and this by defining essentially this form that we can describe x and p of k like in this form. Of course, we can directly express x k plus 1 and p k plus 1 in this form, which is of course just one more k essentially. So it's again this psi vector times mu of k plus 1, or if you like, equals psi times mu to the power of k times or to the power, sorry, times mu, like this. Mu is a scalar, so we just pull out this plus 1, and of course this is the old one. This is x and P at time step K. And by having that, that's actually the meaning of eigenvalues and eigenvectors here. In this case, Xi will take the meaning of an eigenvector and mu of an eigenvalue, and that's exactly what we see. We evolve this vector, and that evolution just scales this this vector when we go over time to the next time step, just scales it by the corresponding eigenvalue. All right, let's just insert this expression into this equation up here, 726. So we get Xi here, and we get Xi and the factor mu here as well again. So Xi times mu, or actually we can use this expression here. Essentially what we'll get is a form like this, X, capital X as some matrix, and Xi as the unknown vector here equals mu, which comes from this one time step that we describe as a scalar eigenvalue multiplied here, times some other matrix Y, which is essentially this coefficient matrix, times Xi. And so Xi and mu are the unknowns, and X and Y can be just constructed from all our coefficients. And that's what we call a generalized eigenvalue problem. Right, so we can solve such a generalized eigenvalue problem. And if the matrix G is non-singular, then what we will get is the following. We'll get eigenvalues. Now, if you look at the size of these matrices, they are 2 by 2n by 2n. So this one is an n by n matrix, G up there. This one is a square matrix, of course, and this one is an n by n matrix as well. So in total, we have 2n by 2n. So we'll get 2n many eigenvalues of this eigenvector equation. And it turns out that we will get one bunch of them, which we call, or we enumerate by mu1 to mu(n). And then we'll get their inverses also as eigenvalues. That's due to the particular structure of these matrices. That we get reciprocal pairs. So we get mu1 and also we'll get mu1 inverted, so 1 over mu1, and so on. And these eigenvalues actually correspond to the eigenvalues of the closed loop system that we will get by solving the optimal control problem. Now, obviously, we will want to have eigenvalues which are stable. So let's say mu1 is inside a unit circle in the complex plane, and mu1 inverted is then, of course, outside the unit circle. It then turns out that by selecting those which are inside the unit circle, we just call them mu1 to mu(n) here. So we select those, and that will be just n many, which are inside the unit circle. And based on the associated eigenvectors Xi, we can construct, we can finish up essentially the control design or the solution of the optimal controller here. And by choosing these eigenvalues, we actually will realize the optimal controller that assigns these eigenvalues. So in the end, we're back at eigenvalues, of course. I told you in the beginning that we will not concern ourselves with pole placements. Instead, we'll look at an optimization problem, but you see how intertwined these worlds are actually. And we only look at this solution when we want to understand algorithms that solve such an algebraic equation. So we can use eigenvalue, eigenvector structures here. Let's see how this goes on, how this actually works out. In the end, we will select these stable eigenvalues, and we will also use Riccati's idea of the sweep approach. So that means that we have this ansatz pi at some time level equals s times xi. And s is taken here. We are in the algebraic Riccati equation. So we say that we look at a stationary solution of s of this matrix S. So we do not have an index there, that's just a constant matrix. And that's the sweep approach that where we just express the pi's as a linear combination of the xi's. And now we will remember we had xk plus I and pk plus I here. So now what we'll do is we'll just replace pk plus I here by s times xk plus I. And we express, as you see, essentially up here, we take this or this, so this form here, and for a particular eigenvalue and for a particular eigenvector xi that we found by solving this eigenvalue problem up there, we will actually be able to recover this this original equation here. And now when we when we insert so we take that apart again. What we try to do now is to actually see that we end up with the Riccati equation. Until now, we did not, we started out with the optimality criteria here, and we worked it into a way explained with eigenvectors, eigenvalues. We solve, or we assume that we solve this eigenvalue problem, so we get particular mu's and xi's as eigenvectors. And now we reinsert that and we use the Riccati sweep approach. And then we expand all these terms again. And it turns out that after some reformulations down here, we will get to a form, or actually up here, we will get something that is a large, complicated matrix coefficient expression times xk plus I collected to the right equals 0. That sounds familiar, right? Because that's how we actually could get to, with the sweep approach, to an expression of the difference equation of S when we discussed Riccati for the first time. So essentially, it really turns out that this equation is exactly the algebraic Riccati equation again. So that was just kind of a proof in the end that we actually worked on the same equations as one chapter before, even though we approached it in an entirely different way. And the nice thing about that is that we can solve, using standard numerical tools in MATLAB, for example, eigenvalue problems like that with ease. That it is really simple to do and efficient, especially. So essentially, one way to solve the algebraic Riccati equation we have sketched now. So we come up with this generalized eigenvalue problem. We evaluate or compute the eigenvalues and eigenvectors, and then we select those which have which correspond to stable pole locations. It will turn out that these pole locations are actually the closed loop poles of the corresponding system. We partition these eigenvectors as we assumed in our approach here. So that's what we get from solving the eigenvalues and eigenvectors. We have that as a numeric vector here. We can split it in half and understand the first one as xi component, the second one as pi component, which we can write as s times xi. And we can do that n many times for the different eigenvalues. So we get n many equations here where we can write down, we have x's and we have s times the corresponding x. Well, we don't know about s yet, but we have this product and we have this vector from our eigenvector surgery, if you want. And we can come up with a defining equation for S by just writing down S times all these vectors, or S times all these vectors are the lower parts of the xi's here that we put to the left-hand side, and so the right-hand side, and on the left-hand side, we will get the lined up column vectors of the xi's in the upper half. So we get this matrix, and these two matrices are now given as numbers, as numeric matrices, and we have an unknown S, and then in MATLAB, we will just take S as this matrix x1 and so on until until xn, and backslash it onto the P matrix to solve this linear system of equations. And that gives you the matrix S. That's how you quickly and pretty efficiently solve the algebraic Riccati equation, even though it has a nonlinear, difficult structure and is a matrix equation in that sense. So let's have a look at a particular example. We take a small system, but large enough to warrant actually a solution like the one we've seen above. So we have a 2x2 system with one single input, and we have unit weightings here. Now we build up these matrices X and Y just by combining the coefficients that we are given. So we get these 4x4 matrices here and solve the generalized eigenvalue problem. It has 4 solutions and 2 eigenvalues inside and 2 eigenvalues outside the unit circle. We take the 2 eigenvalues inside the unit circle, which have these values, 0.29 and 0.266. And associated to those, we will have 2 psi vectors, which are these columns here. That's the result of the eigenvector computation. In MATLAB, you do that just by V and D equals eig. And I think for the generalized eigenvalue problem, it's, don't get me wrong, it's probably X and Y, but just please look that up if that's the correct order of the matrices. Essentially, it's really the eig command, and it will give you the eigenvectors, and it will give you the eigenvalues on the diagonal of this matrix. So that's how you programmatically solve this problem. And then you essentially cut here because you want to get the P matrix, which is the guy down here, and the X matrix up here is the matrix of X components and the matrix of P components. And then essentially you write down S times all the X's, X1 to Xn, equals all the P's, P1 to Pn. And you see that this lines up. That's of course this lower 2x2 matrix is this matrix on the right hand side here. This matrix up here is this coefficient matrix, and then by just computing the solution to this linear system of equations here for the unknown matrix S, just gives you this matrix S. And that's the solution of the algebraic Riccati equation. And using these values of S, you can insert into the control law, and that's it. Let's have a look at an unstabilizable system and what actually happens when you try to solve the 2-point boundary value problem, which if you look into the evolution of S itself, you can only solve it backwards. And we see that this amounts to, in an unstabilizable system, we will not get a steady state solution. It doesn't settle in that sense. So let's see what I mean by that. We have this system. The system has 2 unstable eigenvalues. Well, how do I know that? Remember, we spoke about if a matrix has a particular structure, let's say A11, A12, a 0 block, which goes to the main diagonal, and then we have A22. Then the eigenvalues of such a matrix are the eigenvalues of matrix A11 union the eigenvalues of A22 because of this block of zeros here. All right, so that's one quite useful result from linear algebra. So essentially, we have the situation here, and here you see that the 0 is down here on the left. So that means applying this idea here means that the eigenvalues of this entire matrix are just 2 and 1.1. So I can directly read off them in the main diagonal. I can directly read off the eigenvalues of such a matrix. Okay, and now these two eigenvalues, they are still coupled by this off-diagonal term here. And in this sense here, I write down, I affect the system with the input u on the first state, but the second state, now the problem is that the 0 is actually here, because the problem for stabilization comes up because the second state, if you write it out, x2 k plus 1 equals 1.1 x2 of k, and that's it. So you see that this 0 here actually killed controllability of the second mode, and the second mode is unstable, as you see by the value of 1.1, which is outside the unit circle, while you still can affect the first state's value by the input. The second state is unaffected and will just blow up exponentially, taking the first state with him, because actually in the first state you have the second state's value as well here. So the second state, as it goes to infinity, will drive the first state to infinity, as long as you cannot compensate, which you cannot do for infinitely large amplitudes, of course. So essentially the second mode here is unstabilizable. Let's see what happens if we attempt to solve the matrix difference equation for the Riccati solution S. So we take unit weightings, and since L equals the 0 matrix here, if we don't write it down, right, that was the terminal cost term, we start by S of 7 as the 0 matrix. So 7 is the horizon length in this case that we look at. We can really start at any arbitrary point in time and just look at the evolution of the individual values. Now S is a matrix which is also symmetric from the structure of all the equations. So let's call S11, S22, and then we have S12, and here we have also S12. So we have only 3 different values, and we will see that actually S22, which is this value here, that corresponds here to this signal with the open circles here, the non-filled circles. And it turns out, well, in the beginning, or I should say in the end of our horizon, at time 7 here, everything, all these values in the matrix S are 0, because it's just equal to L in the end. Then we evolve backwards in time, and we will get some non-zero values everywhere. It turns out that in the other 2 values, or in 3 of the 4 values actually here, we will get quickly some stationary behavior. It will get to some, it will become finite, and it will settle without changing the individual values anymore. This is not the case in the value S22 associated to the second state, which grows infinitely without any bounds. And no matter how far we go there, which comes actually from the fact that the second state here is unstabilizable and will just go off to infinity. So that's how we see that, and that makes it plausible that uncontrollable states, unstabilizable systems with uncontrollable and unstable states will yield infinite values in the matrix solution of the Riccati equation. And therefore, we can see that there is no reasonable steady-state solution with finite values. So that's why in this case, for an unstabilizable system, we cannot solve the algebraic Riccati equation. Right. So that was basically under the hood. What happens when we actually formulate and attempt to solve an optimal control problem. Luckily, of course, there are elaborate codes to do all of that you've just seen in MATLAB, in many other computational science languages or packages or software packages. So of course you can solve the Riccati equation nowadays by some standard library tools. In MATLAB, for example, in MATLAB, there are a bunch of algorithms and commands to do that. For example, DARE is a command which translates as an abbreviation for discrete, meaning discrete time, algebraic Riccati equation. And I think you supply, my guess would be G, H, Q, and R. It's important to actually use the D here. There is ARE as well, but that is the corresponding Riccati equation in the continuous time setting. And this Riccati equation is entirely different in structure. It's not entirely, it has similar structure in some sense, but it's not equivalent because there we really are in the differential equation domain, and the Pontryagin principle just looks different, respectively. The stability regions look different, and how we assess stabilization or the integration of costs. So essentially the continuous time algebraic Riccati equation has similar issues, has similar problems to be solved, but in detail the terms look different. So don't mistake one for the other, you will not get the right results. Then there is the, I would say, top level comfort function, LQR, and also here please use DLQR in MATLAB. And also here you have G, H, Q, and R. Actually, I'm not quite sure if the DARE notation is really right. Please check that. I always mark it with a small question mark here for your own, left to your own to check, please. This one I'm pretty sure because I often use it. So you will get the DLQ, by DLQR, you will directly get the feedback gain K, the solution S of the algebraic Riccati equation underlying that, and I think the eigenvalues, so the actual mu's, let's say, the mu vector that is being realized, the eigenvalues of the closed loop. So that's of course convenient because you directly get out K, which you otherwise would still have to insert. So once you've gotten that, you are ready to implement your controller directly. All right, now, of course, the question is, how can we come up with good choices of Q and R, of these weightings back here? And to do that, to wrap our heads around that, let's see in a very simple example, in the simple most possible example, how this complicated Riccati equation is affected and how the solution is affected by a different choice of Q and R. So we look at this cost function in the quadratic manner, so the quadratic cost function with matrices Q and R here. And we will not look at a vector system here with many states, but instead we'll reduce our attention, we'll focus our attention to a scalar system, a scalar state, so a single state system with a scalar A eigenvalue and B term for the input. Of course, B has to be non-zero, otherwise the system is not controllable. And we will, of course, also now have scalar weighting values Q, respectively R, and we'll use lowercase letters to denote that. Here you see that. As you see, this vector notation is not necessary now. And that's actually why we take this approach, because we can reduce all the Riccati equation to a simpler quadratic equation then. Let's see how we do that. So particularly, we'll choose Q and R positive, but we will look at various ratios of these, very small and very large, to look at the boundary cases, what happens in the system in these cases. So the algebraic Riccati equation will become of this form here. This form is still too complicated for a simple solution here. We have s squared, and then we have some term which we invert, so it's 1 over s, and then there are some linear parts, so it's, we actually would have to fiddle around with that. You see how this blows up. This goes just for this simple system, or this simple expression here, we can solve it by some reformulations, but already this is a relatively messy formula for a single state system. Still, that's the solution it specializes to. So we have a quadratic solution essentially, and you see here that all the parameters, of course, go somewhere into the coefficients, into the solution of this quadratic formula, and that the result yields S. We also will have a positive and a negative S here, but for our studies here, we will not need to distinguish that. So what we'll do now is we'll cover two extreme cases. We call them strong control weights, and the next one afterwards will be strong control input weights. So that strong control weights means, the other one is strong state weights. For strong control weights, what we mean by that is that Q over R becomes 0, or in the limit becomes 0, or it becomes very small, meaning that R is just very much larger than Q. So in other words, when you look here into our cost function, that means if R is very much larger than Q, so Q is 10 to the minus 8 and R is 1, for example, then that means that the controller is expected to be very, very careful in the choice of U. It should be very soft there. For the strong control weights, we said that U terms in the objective are very important, whereas X terms are very unimportant. So essentially, the controller is told to not care about where the state of the system is. Instead, do not use U at all, basically. That's the job that the controller is tasked with. Let's see what that means mathematically. So we take this explicit solution of the Riccati equation for the simple case and let Q over R go to 0, and then we do this limit. We have to distinguish two cases now. Let's start with the case that we have a stable system, so that the absolute value of A, of the eigenvalue of the system, is less than 1. Now, if that's the case, we will, after some limit operations from essentially this one here, we'll get to this relatively simple expression. S is approximately Q divided by 1 minus A squared. 1 minus A squared, since A is now inside the unit circle, is some still positive number. So S is proportional to Q in this sense. Then if we insert into the control law, remember there is still some more terms to take into account here. So we get RS infinity inverted, then we get B here, S infinity, that's this approximation that we'll use, times A times X of K. And now that putting that all under one roof will get us this coefficient. and we will see that that we will get x of k multiplied by something that is where we can pull out 1 over r. And 1 over r, if you look at this, let's fix q to be equal to 1, for example, and r to be very, very large. Then 1 over r will be very, very small. So for very large r's here, for a stable plant, here we're in a stable regime, we will see that the controller will essentially output nothing. U will approach 0. U will be very small. And that means that if U is 0, the closed loop dynamics will be the same essentially as the open loop dynamics. We will just simply not care, not change anything. The controller's optimal choice of inputs is 0, so just leave the system in an uncontrolled way. That optimizes our choice of the objective function, of the cost function, which is fine because it's anyway stable and we just do not change anything about it. The best thing we can do when control inputs are infinitely expensive is not use them at all in this case. Now, interestingly, the situation is different when we look at an unstable system. If the system is unstable, it actually is more important to stabilize the system than to have 0 input and hence 0 cost in the input term. We get a different limit here, which looks like this. For A outside or on the unit circle, especially outside the unit circle, then we'll get the term A squared minus 1 here. So also this difference is then positive. So we get R up here in the numerator. Now inserting that gives us a particular feedback law. This one is actually exactly equal to that once we've done this approximation up here. And when we insert that into the closed loop dynamics, let's see what happens. After some, we get, this is U. So after, let's just write this out. X k plus 1 equals A times X of k plus B times U of k. And that's minus 1 over B times A squared minus 1 divided by A X of k. Now, this one cancels. We get a minus here. And we see that actually we get A squared minus 1 over A. Sorry, A minus. So we get A minus this expression X of k. And finally, we get 1 over A times X of k. Okay, so that's actually pretty awesome that we invert the system dynamics, we mirror the pole to the inside of the unit circle. We just said that the pole is outside the unit circle somewhere. And by applying strong control weights, so control is extremely expensive, but we have an infinite horizon. So at some point, even very high control costs would be outweighed by states blowing up to infinity, which would be the case in the uncontrolled setting here. So the optimal choice is use some control action, which is given by this optimal control action here. And by doing that, in the closed loop, you will mirror the pole to the inside of the unit circle, which is actually a very interesting result. So here we have a small example. We get a 4-state system here with a single input. We have various eigenvalues, eigenvalue at 1, which is an integrator pole. We have an eigenvalue outside the unit circle, and we have 2 eigenvalues inside. Now, if we choose R very large and Q very small, then what happens after solving the controller and looking at the closed loop poles is that, so that's this case. We have extremely small weight on the states and very high weights on the inputs. Still, we will significantly change the poles. We will not change 1 because that is its own mirror image. So 1 over 1 is still 1. So the integrator pole stays the same and marginally stable. The other stable poles here have been virtually unchanged. Only this one has changed. It has changed by a significant amount, namely it's just mirrored, it's flipped to the inside. It's the reciprocal value of the open loop pole here. And that's, in this sense, the optimal way the system can be stabilized. Energy optimal, if you want, in the input. Now, for strong state weights, we turn around this ratio, or the ratio is now increased to very large values. So Q is very much larger than R, which means that the states should be considered extremely expensive. And the task that the controller receives is minimize the aggregated sum of squares of the states as fast as possible, because that's extremely expensive, no matter what input magnitudes you use. Sounds familiar? Well, that's it, because if we approximate this, the Riccati solution and insert, we'll get to some particular feedback law, and in the end, we will get a deadbeat controller. Xk plus 1 equals a cancellation of whatever dynamics there was equals 0. 0 times x of k. So essentially, in this limit, we make the controller extremely aggressive. So large Q, large state weightings mean that this controller becomes very aggressive, whereas very small state weightings either leave the stable open loop system completely alone, the feedback gain becomes 0, or the very interesting case, it's just stabilized with a minimal amount of input, which is this particular solution for the unstable system, in which case the closed loop system dynamics becomes, the pole location of that becomes the reciprocal of the open loop pole location, which is an unexpected and surprising result. All right, finally, to sum up the necessities for an LQR controller to stabilize the system, we've seen now that we have several ingredients that we need. When we look at, let's look at one more pathological case. When we have a system, very simple system, which is perfectly controllable and it's marginally stable, so we have an eigenvalue of 1 here, and we can control it. That's a system which is nice to formulate a controller for. We can just stabilize the system and work with it very nicely. However, if we are only interested in the cost function u squared, then, as we've seen before, in our limit, the open loop eigenvalue would just be mirrored. Now, this is already the stability limit, and essentially, it will stay there. We will not improve the situation. We will just get a non-active controller. The controller will just be u of k equals 0, which is not really useful. So in that sense, we failed to apply or to imprint asymptotic stability to the plant. And why is that so? Well, the problem here lies in the fact that we do not see the states themselves. We only see a part of the picture, especially not the state that is marginally stable or unstable, maybe. So we only see the inputs, and that is related to what we call detectability. Detectability is a feature or a property of matrices of the system matrix G and of Q. If you remember our discussion from some weeks ago, I told you that if you have a system output y of k is some c transposed times the x vector, and you write x transposed qx as a state weighting term, then of course you can choose q as c times c transposed, and essentially you would get y transposed times y, which is y squared. So you can understand this weighting matrix in this quadratic form here, C times C transposed. You can understand such a weighting matrix as defining particular outputs that you want to weigh. It just defines the linear combination of states that you weigh together in this quadratic fashion. Hence, compared to controllability or stabilizability, the notions here of detectability, respectively observability, concern the output of the system and the system dynamics, of course. G and Q. And we call G and Q a detectable couple, defining a system which is detectable if for every eigenvalue which is unstable outside the unit circle, we will get 4 particular eigenvectors ui of this matrix G for this unstable eigenvalue, that we can take that as if it was a state vector, this mode shape, if you want. And if we weigh it by the Q matrix, then this weighting or this weighted scalar here, this cost term, would have to be greater than 0. If that's true for all unstable eigenvalues, that means that you can see all these eigendirections, these eigenvectors, these directions in which this eigenvalue is active. And if that's the case, you can see all the instabilities in a system coming up. And then, if that's the case, we call the system detectable. And a fully state observable system is always detectable. But of course, you can have a system, just like in the controllability case, where you cannot see some part of the system, but if that part of the system, if that state is stable on its own, it does not deteriorate or destroy our property of detectability. And finally, the stability of a system controlled by an LQR in the closed loop is dependent on two properties. The system has to be stabilizable, and all the unstable modes have to be detected in the cost function, so the system also has to be detectable. With these two properties of the system, when we design an LQR, then the strong result is that this optimal controller guarantees closed loop stability, at least for that system that we designed it for. Of course, you always have to check if you have model errors. Of course, if the model errors are too large and the system is, the controller is too active, too aggressive, that of course can break things. But in the perfect case, if your system is exactly like you modeled it, then you are guaranteed closed loop stability. And if the system is stabilizable and your cost function makes it detectable. Right, that was it for today. Thank you very much for your question and for sharing and being part today. If there are some questions, we can still discuss them. Right, next time we will finish up essentially this chapter, of course, with some weighting tricks and tips, how you can achieve stability, absolute stability margins, and modal weighting, which is highly useful in practice. We'll go through the last chapter of feedback linearization, and in the appendix next time or the time after that, there is a nice example on an orbital transfer maneuver, where we will encounter what we've seen in the sampling chapter again, and we will be able to solve an interesting orbital problem in that sense. Consider that as a bonus or as some additional outlook material, but it's important. Look into the optimal controller stuff that we looked in, that we went through today. I know it's a complex matter, but it's highly useful in practice, and it's really important that you understand the basics and the application of an optimal controller, and that's that you make yourself comfortable and proficient with using, designing, and playing around with, for example, an LQR in MATLAB. That's essential. Also speaking for the exam, but it's also essential for applying efficient control, model-based control in practice. That's really one of the practically most useful controllers that you can apply, that can yield a very fast, very also quite robust control performance for even multivariable plans.